Buenas tardes y bienvenidos otra vez a nuestro último webinar de este día, 21 de octubre de 2020, de lo que nosotros denominamos en SITEC como el SITEC October Test, dedicado a webinars para laboratorios de prueba y contenido relativo a esto. Este webinar tiene por título Tips para pruebas de vibración en SENO. Será el primero de una serie de 3 webinars dedicados a Vibration Research como tal, tips para pruebas en SENO, tips para pruebas en shock y por último tips para pruebas en random. Ya les estaremos haciendo saber la información de registro para los siguientes webinars y bueno, esta vez nos acompaña nuestro amigo y colaborador Ryan Becker de la compañía Vibration Research. Es ingeniero de aplicaciones internacional para la marca. Muchos de ustedes ya lo conocen. Él es el soporte para Latinoamérica principalmente y para la región de Asia. Mi nombre es Leonardo Bonilla, ingeniero de aplicaciones de SITEC y pues nosotros vamos a estar durante este webinar con la parte del contenido en inglés principalmente. Ryan nos va a estar apoyando y yo simplemente voy a hacer un resumen de las partes más importantes en español. Cualquier duda o comentario es bienvenido en la sección de preguntas y respuestas. Con todo gusto estaremos para contestar las inquietudes que puedan surgir y de sus aplicaciones en específico. Nuevamente les agradecemos. Muchas gracias, Ryan, y bueno, comenzamos.
Yes, thank you, Leonardo. It's great to be here. I'm excited to join SITEC in the October test webinar series. As Leonardo mentioned, this is our first one in a series of 3, sine, shock, and then random. We hope to see many of you at the following events as well. But let's jump in here. Talk about the topics. Today we're talking about sine. So we'll start off by going into sine testing, what, why, and when. So what is sine testing? Why do we do it? And when do we do it? Next, we'll look at minimizing external noise during a sine test. What are some things that we can do to help finish our test successfully? Next, sine profile entry tips. What are some things we can do to avoid mistakes when running a sine test? Next, we'll look at tips for resonance search, also known as a Sine Sweep test. And finally, a way to improve our resonance dwell. So tips for resonance dwell. So first off, let's start with why do we run sine tests? Well, let's look at, well, what is sine testing? So a sine vibration test exposes a device or product to one single frequency at any given time. So of a defined amplitude in time, right? So we can see a sine wave up on the top right. We can see a sine sweep test down there in the bottom right. 2 common types of sine tests are sine dwell and sine sweep. And so we'll talk about that as we move on.
Así es. Bueno, nos referimos a la vibración en seno, una de las más comunes. Y bueno, es cuando colocamos nuestro dispositivo de prueba a una sola frecuencia, amplitud y tiempo, que es lo que define la curva de seno. Los tipos de pruebas en seno más comunes son sine dwell y sine sweep, que quieren decir mantener una frecuencia en un punto, que es el dwell, o sea, mantener, y un barrido de frecuencia. Eso es lo que mayormente nos vamos a encontrar.
Perfect. So as Leonardo explained, the sine dwell is a fixed frequency test. So here we can see we set the test to run at 30 hertz, 1 G, and so we see only one frequency. If this was a sine sweep, we would see this moving here, right? So a single sine wave at 30 hertz. Now a sine sweep, on the other hand, we're sweeping. So what that means is we're changing frequency as we run. So for example, here, this test is running from 30 hertz up to 1,000 hertz. And if you imagine, the way this is set up is our control channel is channel 1, and we have either 3 different products or 1 product with 3 accelerometers. And those are what we call our response, channel 2, channel 3, channel 4. So control and channel 1 are on this flat line, right? We've asked the shaker to run at 1 G from 30 hertz to 1,000 hertz. The response, channel 2, channel 3, channel 4, we see several different resonance points here. So channel 3 had a resonance right here somewhere around maybe 150 hertz. We see channel 2 had one up here around, I'm just going to guess, about 500 hertz, right? But what we see is that we're sweeping through, and what that allows us to do is understand the dynamic of our product. So why should I use a sine test? What is the reason that we're doing sine tests? Well, the number one is what I just talked about. It's we can accurately identify resonances of a product. So for example, in this image on the right, we can see that this product has a very sharp resonance. Its first mode resonant point here is at 192.6 hertz, right? We actually see that there's a big response. I'm not sure what type of product this is, but it's very, very sharp resonance. We have 1 G input with 100 G's output. So it's a very, very sharp resonance. But what it tells us is that if we're designing this product, right, we want to make sure that we're designing the product so that the end use environment does not excite these frequencies here, right? So for example, maybe the end use for this product is 30 hertz to 100 hertz. In that case, most of the product's life will never experience the resonance, right? So product engineers can do this to better understand their product. Next, this can also be an effective means to bring the product to failure. So what does that mean? Well, it means that if we define the resonance point, for example here, 192.6 hertz, we can run a test, a sine test, at that frequency, that fixed frequency, and that's going to be the most damaging test to that product, right? Because we're focusing all of the shaker's power right on that resonance. And so we can use that for a pass-fail test, or we can use it for a fatigue test.
Así es, lo que podemos observar esencialmente aquí en estas 2 diapositivas es el uso del software para identificar las diferentes resonancias que se pueden presentar en un producto bajo prueba. Aquí, como lo podemos ver, tenemos una resonancia alrededor de los 192 Hz y por un lado nos va a servir para definir las especificaciones del producto y evitar que en la vida real este producto se someta a este rango de vibración. Y por otro lado también nos puede ayudar para que una vez encontrado este punto, llevemos a cabo la fatiga del producto en esa frecuencia de resonancia e induzcamos la fatiga del mismo.
Okay, so when should I use the sine test? Obviously here, as we've discussed several times, to identify resonances in a product. That's probably the #1 reason that we use sine, right? We define the response. But we can also use that as well to define or validate our shaker and our fixture. So we can potentially identify problems with our shaker, with our head expander, with our fixture to ensure that it can run the test that we want. So we can do a sine sweep on that. We also have it's a special calculation called total harmonic distortion. And the image on the bottom, what that was we did a sine sweep from 2000 Hertz to 1500 Hertz. And we did it once, just with a normal table. And the second time, we put this wrench on top of the table to simulate something loose, like a loose screw or a loose part inside the shaker. What we can see very clearly is much more distortion in that signal. So one very useful tool that people can use in their lab is every year they can run a sine sweep, or they can run a sine sweep with this total harmonic distortion calculation, and they can evaluate how their shaker is reproducing a signal, right? How well is that shaker running at each frequency? Typically, we say if the shaker is above 10% THD, there may be something going wrong, or perhaps the flexures are becoming old. But it's very nice. You can overlay the past years to confirm if something is changing.
Una muy buena herramienta que nos puede ofrecer también la validación en SENO es identificar posibles problemas que tengamos con nuestro shaker. Eventualmente es un equipo dinámico que al cabo del tiempo se puede ir pues dañando periódicamente, y una manera de comprobar su funcionamiento en cada una de las frecuencias es con el módulo de THD que nos ha mencionado Ryan, que sirve para evaluar directamente cómo se está comportando. En ciertos valores podemos decir que el shaker está, pues ya algunos componentes internos se necesitan reemplazar, y pues también se puede validar ciertas fixturas directamente en los sistemas de vibración con esta herramienta.
Perfect. And finally, when should we run a test? When we want to qualify the test, right? So the photo there you see is a lawnmower blade. And so what we're doing is we're testing how long that lawnmower blade can survive at its resonant frequency, given a certain acceleration. So we can do the pass-fail test, or we can do a fatigue test.
Aquí se ve representado de manera gráfica lo que vimos en diapositivas pasadas, donde podemos inducir nuestro producto, en este caso una viga, a una frecuencia de resonancia y ver cuánto es lo que dura el producto en esas condiciones.
Okay, moving to the next topic, it's minimizing external noise. So minimizing other problems that may cause issues during our sine test. What are some of those issues we might find? Well, one is ground loops. The next is a shaker, head expander, or fixture that is too noisy for my test, right? Because its resonant frequency is being excited during the test. Next is I need to select the correct accelerometer. So if we look at ground loops, what are ground loops? Well, in a vibration test system, we have to be careful to confirm that there is only one ground point in the system, or else we run the risk of having ground loops. So our controller, our amplifier, our shaker should all be grounded back to a single point. When we see problems is people have the controller at some distance from the shaker and it's plugged into a different circuit, which means there's a big resistance between the ground points. And what can happen then is that there is current being pulled through your signal cables, and that shows up as noise on your test.
Así es. Una de las situaciones que debemos controlar con nuestro sistema de vibración es tratar de minimizar el ruido externo que puede producirse por una conexión diferente a tierra entre los componentes. Por ejemplo, el controlador que vemos aquí de manera gráfica, pues está conectado a una tierra que está a otro lugar, así como el amplificador del shaker y el mismo shaker. Entonces tenemos que unificar esas tierras para que el ruido no se pueda presentar directamente en forma de zumbido dentro del sistema de vibración.
Okay, we can verify the resonant frequency of the shaker, head expander, and fixture. And with this section, I would also like to answer Mr. Noriega's question. And so Mr. Noriega asked, can you give us more details about the test we need to run to validate the shaker or the fixture? So the most basic test we can run is a very simple sine sweep, right? And so we can mount our response accelerometers on the fixture, on the head expander, and we can understand how it responds with a simple sine sweep. And what we can do is compare that yearly. If you have access to more advanced calculations, like total harmonic distortion, you can use that to even get a better picture of how well the shaker is reproducing the signal that you want.
Así es. Por aquí en la sección de preguntas nos hacen una que dice que si pueden apoyarme a explicar más a detalle la prueba para validar el shaker y los fixtures, qué módulo se necesita o qué opción. La retoma aquí Ryan debido a que, bueno, la diapositiva se expresa de una manera sencilla. Lo único que podemos hacer, una de las herramientas es correr una prueba en SENO, colocando acelerómetros en el shaker, en el head expander o directamente en el fixture que estamos montando y así confirmar dónde se están presentando los puntos de resonancia para tomarlos en cuenta una vez que montemos nuestro dispositivo de prueba.
Okay, and finally, it's important to select the correct accelerometer for the test, especially when we're running low-level sine tests. So if you're running 0.5 Gs, 1 G, we would recommend that you use 100 millivolts per G or higher accelerometer. So what that means is 50 G max or less, right? A 10 millivolt per G accelerometer has a max of 500 Gs. 100 millivolt per G accelerometer has a max of 50. You can also prevent ground loops by using what's called an isolation base. Now, if you're having problems with a ground loop between the shaker and the controller coming through the inputs, oftentimes this is caused by a ground loop because the accelerometer is getting a ground from the shaker and the ground is not balanced.
De igual manera, los sensores son una parte importante dentro del lazo cerrado que representa el sistema de vibración. Es por eso que para minimizar cualquier tipo de ruido con este factor, tenemos que hacer uso adecuado del sensor que sea correcto. Por ejemplo, aquí hay dos parámetros, más bien un parámetro que nos indica qué sensor debemos usar. La sensibilidad es el factor determinante. Mientras más respuesta tengamos con una menor dimensión en la vibración, por ejemplo, aquí tenemos 100 milivolts por G, vamos a tener la capacidad de lectura de una mejor señal, por así decirlo, en nuestra prueba de vibración.
Okay. There was another question in the chat here from Roberto, and he was asking, what is the benefit of doing a sine sweep test since the random noise you can locate resonances using random by mining the phase change as well as amplitude or the maximum amplitude. The advantage of random noise is that you excite all frequencies at the same time. Granted, you need to collect enough samples to make an average. Yes, that is correct. And we certainly wouldn't say that doing the sine sweep is the only method that you would want to evaluate your shaker. There are benefits to the random method. Over time, if you're looking at a high degree of freedom, you're going to get a very smooth line to know what's happening with the shaker. I guess it's looking more at an average over time. With the sine sweep, we're going to know exactly what's happening at a given frequency. So without any other type of influence, we can know what's happening at that specific frequency, how that's going to influence our other sine tests as well. But I would like to, Roberto, we can follow up with you and we could talk a little bit more about that afterwards. Next, the sign test profile entry tips. So what are some tips that we would recommend when you're entering a sign profile? So when you get a test specification, we recommend that you enter the profile in the units of the test specification. So for example, here in the image on the right, you can see this test specification defines displacement as the control unit for the first portion of the test, and then it uses acceleration further on. We recommend that you enter it directly this way to avoid errors. If you are doing the calculation outside, there's a little more risk of an error when it's transferred over. Next, we also recommend that you confirm expected max acceleration, velocity, and displacement values of the test. So whenever you're running a test, whenever you enter a profile, make sure you double check those maximum values to make sure you didn't type something incorrect. That's a easy way to catch mistakes in a bigger test. Works a little bit better on random, but for sign as well, it helps.
Así es, aquí nos pasamos directamente a la parte de software, donde podemos meter un perfil directamente en nuestra configuración, y lo que tenemos que tomar en cuenta es que los datos de nuestra hoja del estándar coincidan con lo que nosotros estamos colocando. Y una vez eso, verificar si la máxima aceleración, máxima velocidad y máximo desplazamiento son los esperados de acuerdo a nuestra estándar. Eso lo podemos ver en ambas partes, así como se ilustra en la imagen.
Perfect. Okay. And we had a question come in here from Mr. Panchi. He asked if there's any location that we can learn about how to select the correct accelerometer. Is it located in the Shaker manual? This, I would pass the question to the SITEC team because I know that SITEC is working with the manufacturer Dytran, and Dytran is an accelerometer manufacturer. And I know that they're going to have guides, recommendations. So if you can put in, what is this going to be used for? What is the temperature range? What is the frequency range I need? These types of things, they're going to be able to help you select that accelerometer.
Exacto. Así es. Muchas gracias, Ryan. Sí le podemos dar seguimiento directo con usted, ingeniero. Las condiciones que debemos de tomar en cuenta para seleccionar un acelerómetro adecuado va directamente ligado al tipo de prueba que queremos hacer. Sabemos que es evidente, no existe un solo tipo de acelerómetro, no existe un tipo de sensibilidad e incluso la forma cambia. Entonces tenemos que saber si su prueba va a ser dentro de una cámara climática con un shaker, por ejemplo, si su producto tiene espacios inaccesibles, por ejemplo, también, cuál es la manera de montaje que podemos emplear y cuál es el rango de vibración que vamos a tener para así seleccionar la frecuencia, más bien la sensibilidad, perdón, adecuada. Entonces, todos esos factores influyen. ¿Para qué? Para que el sensor sea el adecuado.
Okay. Next, we'll move on to tips for resonance search. And so this will look at when you're doing a Sine Sweep, a resonance search, what are some of the things you can do that'll help prevent issues? So if you've already taken care of all of the external noise issues that we talked about earlier, you're still having problems running that test. What are some things, some tuning parameters that I can change inside the controller to allow me to run that test so I don't get the abort? One is we can lower the sweep rate of the test. We can increase the response time parameter, and we can also increase filtering as well. So we're removing any type of harmonics or noise from the test outside of the desired frequency range. So if we look at lowering the sweep rate, well, what do I mean about sweep rate? The sweep rate is how fast we're moving between the frequencies, right? So if we're going from 10 hertz to 100 hertz, how quickly do we do that? Well, If we lower that down, it's typically rated in octave per minute. So you'll see on the right here, this is 4 different sweeps we did. This one is 0.1 octave per minute. That's the lowest sweep rate. Here is 6 octave per minute, and that would be the highest sweep rate that we used. If you look at this carefully, you can see that we got slightly different resonance locations despite using the same product. So what that tells us here is that sweep rate is affecting our response, right? So what we can do is improve the sweep through sharp resonances, but also increase the accuracy of that sweep by slowing down the test. And this is why you'll see some test specifications for 0.1 octave per minute or 1 octave per minute, because it's going to provide a more accurate result.
Ok, esto es bastante interesante, cómo se ilustra, ya que nos comprueba que si nosotros hacemos un barrido en la frecuencia con una velocidad más baja, en octavas por minuto, como se representa aquí, podemos encontrar de una manera más precisa la frecuencia de resonancia, tal como se puede ilustrar en la gráfica de color rojo, donde está a 0.1 octavas por minuto. Las demás están oscilando en ese punto, pero ese punto es más preciso, es la frecuencia de resonancia más cercana a lo real. Entonces, un tip que sirve para encontrar mejor la resonancia en un barrido, pues es hacerlo más lento. Es bajar el sampleo, por así decirlo, de las octavas por minuto y encontrarlo de una manera más precisa el punto que queremos.
Okay, next. And this has different names and different controllers, so you may need to look up what this is called in your controller. In vibration view, we call this response time. And what this does is it tells the controller to look at more data before it makes a decision to change the drive, right? What this can do is increase the stability of our sweep. And so what happens is if you're looking at your system and you see that the control is very messy, looks very noisy, what you can do is come in here and you can increase that response time, and that should clean it up, right? Because the drive isn't changing so quickly based on little changes in the response.
Así es. Podemos incrementar el tiempo de respuesta que está otorgando el controlador para que los cambios de respuesta no sean tan rápidos del drive hacia el shaker. Entonces podemos tener una mejor comprensión de lo que está pasando directamente en el shaker.
Okay, perfect. And our final tip here is to apply what we call tracking filters when running a sine test. And what this does is applies a bandpass filter around the current frequency of the sine test. And that bandpass filter moves with the current frequency that's being output. What it does is it removes the unwanted harmonics and noise from your test. It isolates the pure sine tone for a more accurate reading. So we would recommend, if there's any type of filtering that you can do, this is why the data can be a little bit inaccurate if you're just looking at the full FFT coming back from the data, because it's not being filtered.
Así es, también podemos programar filtros para que las frecuencias que estén antes o después de nuestro punto deseado se puedan omitir, tal como vemos en la imagen. La parte central es lo que está simulado como una señal filtrada. No es así las que están a los costados, donde podemos tener influencia de otras frecuencias indeseables.
Okay, next, tips for resonance dwell. So resonance dwell is when we sit at one frequency. So traditionally, there's a test called sine resonance track dwell. This is where you would run a sine test and find the frequency, find the resonant frequency, and run the test at that frequency. Well, there's a problem with that. The issue is that the resonant frequency changes as a product starts to fatigue, right? So in the real world, if we're trying to do a fatigue test using a dwell, right? In the real world, if the product starts to fatigue and the resonant frequency changes, well, it's still being excited at that new frequency, right? Because in the real world, there are many frequencies being excited at once. In our lab, we're only exciting one at a time during a sine test. So what is the solution? Well, we need to track the resonant peak instead of the frequency. So here's an example test setup. This is just a small setup, but an example for you. We have a VR controller with 2 channels, a small shaker. Channel 1 is the control accelerometer mounted in the center of the beam, and channel 2 is the response accelerometer mounted at the end. And so the traditional method of doing a frequency test, we would call the fixed frequency dwell method, is you would perform a frequency sweep in the desired range. So at the bottom here in the image, we see 30 hertz to 2000 hertz, right? We did a sine sweep, and then we looked at the peak transmissibility, or essentially the peak difference between the input and the output. We analyze the results and we get that frequency. So let's say this is 150 hertz. And then we just run the test at a single frequency. But what is the issue with that? What are the potential issues with the traditional method of fixing one frequency? Well, as the product starts to fail, the resonant frequency can change. So if we look at the image on the right, so we can see this is our original test, right? So our original test, we did a sine sweep, and we found here this shape, right? 35 hertz was the product resonance, right? So what we did is we set our test to run at 35 hertz, which causes the product to run at, let's say, 10 Gs during the test, right? That's the response. But the product starts to fatigue. And so what happens is the resonant frequency shifts from 35 hertz to 33 hertz. Well, if we're still running our original test, but the resonant frequency shifted, now that product is only being excited at 2 Gs instead of 10 Gs. But in the real world, this product would still be excited here at the full peak at 33 hertz, right? So that's the potential issue with this.
Así es, este es un punto muy importante que tenemos que considerar y que podemos utilizar con nuestro controlador y el módulo de Vibration Research, en donde tradicionalmente lo que hacíamos era encontrar la frecuencia de resonancia y poner a vibrar nuestro producto hasta fatigarlo en esa frecuencia todo el tiempo. Lo que sucede en la vida real es que cuando empieza a fallar nuestro producto, la frecuencia de resonancia va cambiando hacia abajo o hacia donde por ahí se encuentre, puede ser hacia adelante también. Y lo que hace este módulo es recorrer la frecuencia de vibración sin necesidad de que nosotros lo modifiquemos manualmente. Lo hace de manera automática y, por ejemplo, si la frecuencia de resonancia la encontramos a 35 Hz, cuando empieza a fallar el objeto, se va a mover hacia 33 Hz y ahí va a continuar vibrando para fatigar el producto.
Yes, okay. And so finally, what is the solution to the issue we just described, right? As Leonardo described, we need a test that can do peak tracking. So what that means is as the product fatigues, it's going to change the frequency so that we continue to track that peak as the product fatigues until it fails, right? So peak tracking allows the controller to adjust the phase and frequency to maintain peak transmissibility through the sine test. If the product starts to fail, the controller will also shift in resonance. And so in a minute, I'll actually open up our software and show you a little bit how we do that. I'll walk through a whole sine test and kind of talk about some of the things that we talked about today. Okay, before I switch to the software, I just wanted to check if there are any more questions about what we talked about before I do a quick session inside of the software. Roberto asked an interesting question here. He asked, when testing a given structure, is there always an anti-resonance between two resonances in the frequency domain? Put in another way, if we see two peaks with no valley in between, will this trigger a signal that there's something wrong with the test? In my experience, I have always seen an anti-resonance. So I would need to pass that question to our PhD and software engineer and see what he has to say. But Roberto, what we should do is I should get your email, and then I'd be happy to follow up on these two questions for you. I don't know the answer to this one here.
Ok, muchas gracias por sus preguntas, ingeniero Roberto. Bueno, todos las podemos ver por acá y ya les estaremos compartiendo más información acerca de lo que comenta de las antirresonancias a su correo electrónico que ya tenemos por aquí en nuestra base de datos. Gracias nuevamente.
Perfect. Okay, so the first thing I'd like to talk about here is this system check mode here. And this gives you a live reading of both the frequency and the time domain. And so if you're doing that ground loop testing, what you can do is come in here, because the ground loop will often show up as 60 hertz noise. So you can come in here and readjust the way that you have the system grounded and see if you can lower that, that 60 hertz noise. That's one easy way to troubleshoot. Next, I'll go in and let's run a sine test. So I'll start a new test, sine. Actually, in this case, I can run a simple test. That's fine. We're just going to run, let's do from 30 hertz up to 1,000. 1G acceleration is just fine. Now, if you remember what I said about sweep rate, we're going to be more accurate if we lower that value, but we don't want to wait here. So I'm going to increase it just so we don't have to wait. We'll do one sweep. My control channel is channel 1. And then I want to turn on this sine resonant track dwell option. What this will do is automatically find the resonances and allow us to do that peak tracking mode that we talked about. So I'll click OK. Don't need to save the profile. What I'm going to do here is start the test. And I'll come in here and let's add a few channels. I'll add channels 1, 2, 3, 4. I don't need the previous sweep. So you can see we're sweeping very quickly. We can see a few resonances here popping up. And one thing to mention is right now I'm running this software in our demonstration mode. And so one thing that's very nice about VR is that anybody can download this software directly from our website, and you can run all the tests you'd like, all the modules, create profiles, all for free. We use it as a training tool. So here you'll see what it did is it located 2 resonances. And so we see it found one here at 141.7 hertz. We found another one at 509. And so in the traditional SRTD test, I would just enter how long I need to run this, maybe 1 hour or 2 hours, depending on the test specification, and I would run, right? But in our case, we want to introduce this phase control. And what this is going to do is allow that tracking that we talked about. So I will hit run selected tones. And so you see now it's automatically running at 141.69 hertz, what we expected. And what it's doing is trying to maintain this phase. But what we can also do is add this peak tracking option. And what that will do is automatically adjust to make sure that we maintain the peak. And one way we can see that is by looking at this transmissibility graph. So I can add that. We can look at transmissibility, and we can also look at transmissibility versus phase if we like, to see how the transmissibility responds as we adjust the phase and the frequency. So what we can see is this is this automated mode, and what it's doing is cycling by slightly adjusting the frequency. So here, I'll pull the frequency over here so we can see it. Well, now the frequency is fixed. Well, there it starts to go, changing little by little as it's finding the peak. So we see the phase change, the frequency change, all to try to maintain the peak transmissibility of the test, right? And so this is a way that if you were running a long duration test, if the resonance started to shift of your product, what it would do is follow that. Okay.
Así es, solo comentar que el software que estamos viendo es Vibration View, la última versión, y esta la pueden descargar sin ningún costo directamente en la página de Vibration Research, aún no teniendo el hardware, el controlador físicamente. Pueden descargarlo, usarlo en modo demostración, generar perfiles, generar lo que está haciendo aquí Ryan, seleccionar los parámetros que deseamos ver, únicamente como referencia. Se utiliza mucho en universidades, en cursos que se llevan a cabo para conocer fundamentos básicos de la vibración.
Perfect. So in addition to the software, of course, I know that you're all taking this webinar, so you have interest in learning more about vibration. Every topic you can possibly imagine is available on our website. And so I just want to show you some of the resources that we have. Pretty much about 2 times a month, we'll do a live webinar. After we finish that, we'll put that information on our website for free. So these are about 35, 40-minute videos that cover every possible topic in the software. And this it shows you how to use the software. It shows you tips of how to run tests. So if you'd like to learn a lot more about Sine, you can go in here and watch this Fundamentals of Sine. Also, we have Vibration Research University as well. And that's free online classes that teach you about vibration. It's just a lot of great resource. Our VR blog as well. This is a great place to find more information. So for example, if you're looking for shaker validation, you can type that into our search. Try to spell here correctly. And you can see we have several links here. Demonstration mode, common vibration test issues, kurtosis, when should I use sine vibration testing? So that's similar to the presentation I gave, dynamic range. But I think this method for shaker validation is the most useful one. And here it gives us a video that talks about the total harmonic distortion, how to use that, why it's important, and so on. So I hope if you walk away today, if you only walk away with one thing, hopefully you know that our website is full of resources And if you have any questions at all, be sure to send us a question at Vibration Research or SITEC as well, locally in Mexico. They're also running tests in their own lab every day. So they're very familiar with the equipment, very familiar with vibration testing. So just want to thank you all for attending. And we will stay here for any questions that you have, but I'll let Leonardo finish us up.
Así es. Bueno, tal como lo comenta Ryan, nosotros podemos brindarles el soporte sin ningún inconveniente en cuanto a alguna duda que tengan acerca de las pruebas de vibración. Y como también bien lo menciona, pues estamos muy familiarizados con las pruebas aquí en nuestro laboratorio en Querétaro. Usamos el software de Vibration View día con día con nuestros ingenieros de pruebas, y no solo eso, también podemos ir hasta su laboratorio y hacer diagnósticos, mantenimientos preventivos y correctivos a sus shakers electrodinámicos, calibraciones de sus sensores, reposición de cables, de accesorios. Tratamos de cubrir toda la parte de servicio en cuanto a sistemas de vibración, así como lo hacemos para otros proyectos. Bueno, por aquí también me gustaría compartirles la agenda que se viene directamente en los próximos 2 días, si se alcanza a ver. El día de mañana vamos a tener a las 11 un webinar de medición de voltaje presentado por Viewsoft, una de nuestras marcas representadas de sistemas de adquisición de datos. También vamos a tener aplicaciones para detección de fuentes sonoras. Este es un nuevo desarrollo creado por Acoustic Camera y va a ser presentado directamente por su gerente general, el ingeniero Pablo Ayosa de España. Y por último vamos a tener fuentes de poder programables para laboratorio de pruebas, presentado por Brian Xu, que es el gerente de PRIN en Estados Unidos. Posteriormente, para el día viernes, tenemos sensores acústicos robustos para pruebas de NDH, con el ingeniero de soporte global para GRAS, Santiago Reyes, que nos estará dando soporte. Y a la 1 de la tarde tenemos una charla por parte de la gerente de calidad de SITEC Lab, con el tema importancia de probar en un laboratorio acreditado. Y como último webinar de la semana, tenemos otra vez por acá con nosotros a Ryan, con esta vez el tema de pruebas, de tips para pruebas de vibración en shock. Entonces, bueno, pues esperamos contar con su valioso apoyo y presencia en estos webinars que sean de su interés. Recordarles también que es extensivo hacia todo su equipo de trabajo y pues es gratis. Y bueno, pues lo que tratamos aquí en SITEC es de llevarles los mejores temas en esta pues, reunión virtual que tenemos. Anteriormente lo hacíamos de manera presencial. Le ha tocado a Ryan venir por acá, a Querétaro, a Monterrey, a diferentes partes donde tratamos de estar con ustedes. Esta vez lo hacemos de manera virtual por la situación ya conocida. Agradecemos mucho su presencia nuevamente y si hay más preguntas en las que les podamos ayudar, por favor no duden en hacérnoslas saber, tanto ahorita como posteriormente a través de nuestros correos electrónicos o alguna llamada a nuestro teléfono celular. Muchas gracias, Ryan, y esperamos el siguiente webinar.